Hi, my name is Lauren, and I'm really interested in biotech, specifically neuro-oncology, seeing how we can leverage AI and other alternatives of deep learning to help cure brain cancer and specifically high-grade gliomas. So today I'm going to show you a brain tumor classification model that I built using machine learning. And essentially, I found kind of an open source project already pre-existing, and I trained the model, and we trained it. We, myself, and the code. And thanks to the tutorial that I found, this was based off of. I'll link it down below. Same with the GitHub repository where I got the inspiration and the base code from. But basically, I trained it with three different types of tumors. We had pituitary, which is a pituitary adenoma. We had meningiomas, and then we had a glioblastoma. So it's basically kind of three different brain tumors or gliomas, but I guess you could kind of correlate that with glioblastoma. Anyways, enough of me talking. Let's dive into it, and I'm going to just break down a little bit of the code and show you the results that I got from the classification models. Hey, it's Lauren back again. So some main kind of things that I didn't mention previously that are important to note is for this specific model, it's only trained on 2D MRI images. While that is something that in this model worked particularly well, just based on the training data that we had, ideally in the future and with a couple other projects I'm trying to build, we want to move less from a 2D model and more to a three-dimensional end result. Just because when you're actually doing preoperative planning, it's very, very difficult to get the accurate kind of parameters for understanding the critical structures that may interfere if you're going to operate and access these tumors that are in really critical structures in someone's brain, especially when you're operating these high-grade gliomas, particularly which glioma prediction is very relevant. So actually our high accuracy for glioma prediction, this is a really good sign and signal that this technology could be really useful for preoperative and postoperative planning. Also looking at like MRD, so minimal residual disease, is really a good kind of thing to look at for post-operative results. But if we're talking more in the pre-op kind of planning perspective, glioma prediction being kind of high is a great result from this. This is just a confusion matrix and the plot. So I'm going to dive into a little bit of the code. This essentially literally is just the code that I forked from one, the tutorial, and then two, it also has my own results that I got from downloading and training the model based on the source code. But my test accuracy was actually improved from the initial test accuracy that the tutorial had that I was following. So yeah, theirs was 92. I had 94. So we love that. So basically, I didn't totally dive super deep technically into the confusion matrix, but basically it's just saying to see how well our model, our data fit the model and how accurate our accuracy was based on the like false negatives or false positives. So like I said, the glioma prediction is quite high in both the prediction and target. So that's amazing and definitely something we'd want to see more. And you can just, go through the code. I'll link the repository forked that this is referring to. Most of this, again, is just, this is setting the model evaluation mode. So calculating, loss. I'm not going to read directly because it's just based on the code. So you can kind of read it as it's kind of self-explanatory. So our validation accuracy, not the best, but it's still not horrible. Essentially, again, just running through the code, training. This is saving the model after the training was finished. This is setting the training configuration parameters. So yeah, again, saving it again. Here is a lot of lovely code. And this is essentially building the base of our model. So you can see that there's a transfer learning model used and then also setting the parameters. This is super important in understanding our resonant model. So this is like having the different layers in part of what is mainly contributing for our classification problem. And then this is how you train it. Lovely. Again, just talks about the model architecture and more kind of details about that. This is creating the custom dataset class. So this was basically used with the PyTorch data loader. that was kind of built into this. And then this is really good because it's loaded and trained like within real time, as I mentioned. So it can catch like the samples to help better like understand in a memory sense. So say that if there's a rapid change, maybe when you're doing like a patient case and you're scanning the models, you don't have time to completely, start from scratch for your custom for a normal data set class. But if you have it trained in real time, it's much more applicable to settings where maybe it's more less resource intensive, and you don't really have time to kind of go off like pre-existing approaches, but you just have maybe this one program. And hopefully in the future, people like myself can work on building these programs that can be more efficient for clinical use cases and not just only relevant for kind of CS people, but we can make it more approachable in a clinical setting and more approachable for physicians and their patients to understand this data. So while this is kind of very technically dense, it's definitely not going to be the end and be all of the result of this kind of space. And I think that's really important too. And something that I wanted to just kind of give with this really basic, brief kind of project that I did, just kind of like testing the waters with, developing and programming. This was a really fun, not even experiment, just like program to run.